Good afternoon, class. Presented before you is the SEAL AA3 Auto Analyzer, and my name is Patrick. I'm your TA. I'm here to talk to you about it. So this is the machine a little more opened up. This is what it looks like when it's not running, unlike the video I just showed you. As you can see, all of the glass tubes are clear, and those glass tubes are actually what different reagents and your samples flow through to end up over all the way at the left side where there's a sensor that can actually detect any color changes that have happened to your system. And those color changes are what are associated with your nutrient quantities. So we'll be able to talk more about that later when I show you some of those color changes and the way that the software interprets it. But all the way here on the right-hand side, that is actually the arm or probe that will go in between your different samples. It operates in a pretty stochastic manner, but it's a really neat machine. Right there is the peristaltic pump. This pump actually drives the motion of fluids through the system. It kind of presses against the tubes and massages them and moves all the material forward. This happens at a relatively constant rate. Therefore, to alter the volumes of liquids that are actually being moved through the system, we use the inner diameter of those tubings. So the different colors of those tubings on either end kind of tell you the size of those tubings and actually let you know how much of the liquid is flowing through it. Smaller diameter tube means less liquid. Larger diameter tube, like the one that I just had in my hand there, that's just for the water bath, that is going to allow a lot more liquid to move through. Some of the reagents are not very easy to prepare. Some of them can take a little bit of time or working with really acidic or caustic material. So you don't want to have to remake them all the time. And using some tubings that are smaller in diameter allows you to use very little amounts of your reagents. For example, I had a run the other day that lasted about 7 hours, and I only used about 150 milliliters of one of my reagents, while the other I used about 600 mils. So you can kind of see some of them just get used up a lot faster than others. That right there is actually our cadmium coil. So the cadmium actually allows all of our nitrate to be reduced down to nitrite, I believe. And then that can be detected through coloration. So this is me closing the pump right here. You could see by this clamp action, you actually are just sealing those tubes there based against a base plate. All right, that's nice and closed. We're good to go. We're going to start the software, and now we're turning on the sensors. We're going to then plug in the water bath. That's the next step right there. I didn't do that because it's not turned on yet. You then turn on the pump housing, and lastly, you're going to turn on this robotic arm. As you can see, that starts moving the probe around as it calibrates itself. The arm actually is going to move to all of the furthest positions that it can to either get to a cup sample or to get to a standard stock solution. So it kind of has this full 360-degree calibration test just to make sure there's nothing in the way. If the arm does hit anything while this is running, the machine basically just stops all functionality. I haven't found a way to get it to start on its own other than a hard reset, so if you're ever actually running your samples, you got to be really careful not to bump into that arm. Okay, so this is the software side of things. I've got a little more things put together as well, and you can see that color response. So that blue coloration right there, that's associated with ammonium. And this red coloration here, that's associated with nitrate. And you can kind of see a slightly irregular bubble pattern happening. This is pretty common when you first start the machine up. That's a little bit of a clearer bubble pattern and much more consistent. Alright, so I just wanted to take a second and show you guys these colors, the bubbles moving through the tubing, and explain to you a little more about why they're important. So our samples have a lot of nutrients in them, or maybe they have a very little bit of nutrients in them, and the way that we're actually going to detect that is quite similar to the use of a pH strip, which is through color change. So basically, we're pumping through a lot of colorless liquid through this system, and by interacting with the nutrients that we're trying to quantify, it actually exerts a color change that can be detected by a sensor and displayed on a screen. So I'm going to show you what that looks like right there on that screen. Right here we have the machine fully set up. It's running. The probe arm is starting to move to the samples, and you could see on this screen right here this kind of escalating linear pattern. And what that is are the actual standards that have been pumped through the machine at a low level and a high level. And this standard curve that develops is relatively linear, and it kind of just tells you how correlated the machine is to that curve with the known standard concentrations. And you want to look for like a 1.0 correlation, but what you end up really with is like a 0.99 something usually, which is very, very accurate. And this is all based on how strong your expected nutrients are going to be in your solution. So if you can expect that maybe your nutrient profiles are going to be higher in concentration than your highest known standard, then you're going to need to dilute your solutions to actually get them within the detectable range of this machine. So those two curves that I'm pointing my cursor at right there and that last one, that's the highest known standard for that analysis for ammonium right there. That's actually around 8 ppm, just to let you know. So anything above 8 ppm, in theory, could be a lot more than 8 ppm, and I have found that ammonium in particular maxes out around 12 or 15 ppm, and I've diluted those samples down to a realistic range of around 20 or 30 before. So that high peak right there is known as drift, and that smaller one in the middle is known as QC, or quality control. Federal labs are required to include a quality control every 10 to 20 samples, I think. We're not a federal lab, but I still have to run my samples with a pretty high level of accuracy, so I include them at least every 20. And I include that high peak, what's known as drift, about every 20 samples as well. So basically the machine, as it goes along and it's processing things, it can kind of lose some of its ability to detect at that high range. So by consistently kind of checking if it can, you can account for any drift as it goes. And you can see that color response there is a little strong, that bright pink color. This particular sample isn't really exerting a color response for ammonium, so it probably doesn't have a lot of that. That line, that tube right there, is actually what's delivering known as sulfanilamide, which is the color reagent used in this analysis that actually forms that pink color. And if the pink is kind of too strong or too dark, the machine kind of just gets saturated and maxes it out, much like ammonium does at a point above 8 ppm ammonium. So you can kind of see here, these are actually going above the detection threshold, and that red bar right there is telling me that this incoming peak for that high pink sample we just saw is going to be way off the charts. Okay, so right here, you guys can see the trays that actually hold the samples that I process through this machine. And what I'm doing right now is I'm actually preparing them for dilution. I guess you could see from that last clip, sometimes these samples come in way too high. They're coming in at a rate that I really can't quantify the nutrients in the sample. So that could be because I got a really low volume, it's really concentrated, it could be for a number of reasons. That being said, I need to dilute them, and increasingly I need to dilute more than half of my samples to really get a good reading. And I dilute all of them just to kind of make it easy for myself to compare them, as realistically speaking, if I'm diluting 2/3 or almost 8/10 or 4/5 of my samples, I could really start to run into a bottleneck in terms of workload. So I might as well just dilute them all, make it easy for myself, and that way I can get a really nice resolution on both the lower end samples and the higher end samples. This machine allows me to mechanically dilute my samples, so I kind of just choose the size of the pipettes that are installed. I tell it how much water to draw, how much sample to draw. It effectively dilutes it. Generally, I do a 1 to 5 dilution, but if things are really hot, I'll do a 1 to 10 dilution. Those just go right into those new cups. And I'm actually going to play you a little video of the machine priming so you could hear the beautiful orchestra of sound that it makes while it's operating, and get a chance to understand what it's like in the lab. Alright, so right now I'm priming the machine. There's a reservoir of deionized water to the left, and there's an ejection reservoir to the right, and basically this is just warming up the machine. You can see on the left-hand syringe, I've got a 2,500 milliliter syringe. It basically pumps the full size of both of these syringes to capture the full range of motion capable by the machine, and it kind of just warms it up in this primer sequence. And what this is actually doing, when I take this pen and I take it out and I use this little pen to dilute my samples, it's going to remove a certain amount of sample fluid with this syringe, and then it's going to remove a certain amount of water through this syringe. And then it'll eject this syringe first, followed by this syringe, which basically ensures that all of the samples are removed, followed by a very precise amount of water, which allows for very, very clear, clean dilutions. Alright, so now that we've made it through that noise, and I've diluted my samples, I'm going to go ahead and get this machine up and running. So I just wanted to show you guys one last time what it looks like when it's all put together, and more importantly, what it looks like when you have all your reagents organized properly.
So if you have any questions about the specific chemistries that I'm working on here, I'd be really happy to talk to you about them. Just shoot me an email. I have been doing this for years now, for at least 2 or 3 years, so I've become very, very acquainted with the process and know all about it. Thanks for watching. I really appreciate it.